we're now going to look at the idea of an inverse of a matrix. And in order to do that, we need to start with the idea of the multiplicative identity. When we're talking about real numbers, the multiplicative identity is 1, since a times 1 is equal to 1 times a, which is equal to a for any real number a. So we want to try to mirror this for the matrix identity. So I want a matrix I such that a times I is equal to I times a is equal to a for any matrix A. So IN is going to be the n by n matrix with 1s on the main diagonal and 0s everywhere else. And this is our multiplicative identity for matrices. Most of the time we're going to just call this I and we're going to drop the n because most of the time it's going to be understood what the size of our matrix is. And as some quick examples, I have the 2 by 2 identity and the 3 by 3 identity matrix here. We're going to let A be an n by n matrix. And suppose R is the reduced row echelon form of A. Then we know either R has a row of zeros or R is equal to the identity matrix. So let's see if we can prove this. We know that since R is n by n, it has to have n pivots or less than that, since n is the number of columns. If R has n pivots, then it has to be equal to the identity. N pivots means it has to have a 1 in every column, and thus every row. And then the zeros above and below have to be 0, which is exactly the identity matrix. Otherwise, if n does not have n pivots, it has to have less than n. So at least one column has no pivot. And since pivots are also defined as the leading ones in a row, that means at least one row does not have a pivot. And if at least one row does not have that leading entry, then it must just be all zeros. Therefore, we would have a row of zeros. Now that we have an identity, we can actually talk about an inverse. With real numbers, I know that if a times b is equal to 1, then b is equal to 1 over a. And that's the idea of the inverse in real numbers. But with matrices, we don't have this idea of division like we do with real numbers. So instead, I'm going to think of it as b is equal to a to the negative 1. So now that we have this idea in real numbers, let's try to make the correlation with matrices. With inverses, we say the inverse of a square matrix A is a matrix C, such that A times C is equal to C times A is equal to the identity. When we're dealing with real numbers, there are numbers that don't have an inverse. In particular, there's 1, 0. I can't have 0 times something equal to 1. And we do have an extension for that with matrices. We call these singular matrices. So a singular matrix just means it does not have an inverse. While the only number that doesn't have an inverse is 0, there are going to be lots of matrices that do not have an inverse. So if an inverse of a matrix A exists, it is going to be unique, and we denote this by a to the negative 1. So let's actually prove that this is unique. Let's suppose our matrix A has 2 inverses, B and C. By definition of the inverse, this means that A times B is equal to the identity matrix, and A times C is equal to the identity matrix. Since they're both equal to the identity matrix, I have that AB is equal to AC. I can then multiply both sides by B on the left. I know that matrix multiplication is associative, so I can move my parentheses around. Since A and B are inverses, I know that B times A is equal to the identity. That tells me that IB is equal to IC. And since multiplying by the identity gets you back to where you started, I have that B is equal to C. So therefore, I have that this is unique. I started with 2 and showed that they had to be the same. Here I have 2 matrices, and I want to check to see if they are inverses. So I need to be able to multiply them and get the identity. I do this by multiplying the first row by the first column. 2 times 8 is 16, and 5 times negative 3 is negative 15. I then multiply the first row by the second column. 2 times -5 is -10, and 5 times 2 is 10. I then do second row, first column. 3 times 8 is 24, and 8 times -3 is -24. Finally, I do the second row, second column. 3 times -5 is -15, and 8 times 2 is 16. Simplifying then gives me 1, 0, 0, 1, which is my identity matrix. So far we're looking good. Since matrix multiplication is not commutative, we do need to check the other direction of multiplication as well. So I switch the order and do it again. 8 times 2 is 16, and -5 times 3 is -15. 8 times 5 is 40, and -5 times 8 is -40. -3 times 2 is -6, and 2 times 3 is 6. -3 times 5 is -15, and 2 times 8 is 16. So I get the identity matrix once again, so yes, these two matrices are inverses.